So welcome everyone to lecture 21. We'll conclude our discussion on generalized gradient descent by culminating our use case of generalized gradient descent through the projected version. Um, but to be able to take the projected version to logical conclusion, we'll need to just introduce the Karush-Kuhn-Tucker necessary and sufficient conditions. And thereafter we'll be done with this topic more or less. Of course, I'll be pointing you to a lot of optional extra reading material in case you want to know the geometric insight into how these KKT conditions are necessary and sufficient. In fact, not just KKT conditions, but we'll also talk about duality. So yeah, all that will be possible only through extra material. Okay, so this is the part that we'll do today. Projected gradient descent, constraint optimization. I gave you some food for thought as homework, and then that lead us to constraint optimization, duality and KKT conditions, and really a summary of this is all we'll provide. What I'm excited to show you is uh, not just the next topic of discrete combinatorial optimization, how it builds on what we have discussed, but also we'll have lots of libraries that you can play around with. Okay, so the generalized gradient descent was about identifying this proximal step with respect to any routine update you may have. The Z is any routine update. This could be the accelerated gradient descent or any of the stochastic variants. What we saw is that by setting the Cx to 0, you got gradient descent. Whereas if you today, what you'll see is when you set Cx to an indicator function, you will get something called the projected gradient descent, which I had kind of left as homework. Okay, so summary of the proximal gradient descent is that proximal gradient descent becomes gradient descent if C is 0. And if f is 0, one can minimize a non-differentiable function C as long as the prox operator is easy to compute. Okay. And we also saw if prox can be efficiently computed, great. But if it can be only approximately computed, then your overall result will be as good as the prox approximation. Yeah. Now I give this as kind of food for thought. If you have a constraint optimization problem, f x to be minimized such that x and c, a simple modification to the gradient descent procedure would have been to just do the following at every iterate. You do your routine xt minus alpha gradient fxt, and xt plus 1 could have been projected into the set C by a projection operator applied on yt plus 1. Okay, so this is the idea, and you can see an illustration of the same here below. The pink region is your C, and you have seen how there's an update being made. Okay, this is your C. Bit of a problem with the yeah, so this is your C, whereas this point is your xt, this point is your yt plus 1, which you project to xt plus 1. Okay, but this is very intuitive, but this does correspond to the proximal operator. So projected gradient descent is exactly the same as proximal with indicator function in place of C. That's it. Okay, so let me know if you have any doubts. Otherwise, it's pretty straightforward, and this is what I wanted you to kind of give some thought to as homework. So, so this is why projected gradient descent is a special case of proximal gradient. And in fact, all results for standard gradient descent carry over to the projected case as long as the projection operator is easy to compute. Now, this is where the caveat is. How do you compute this? And it'll be really unfair to now, leave you wondering about it. And that's why we have brought in duality, KKT conditions, and so on in a very brief manner. So this can be possible through KKT conditions, then necessity and sufficiency, duality, Lagrange dual, more specifically Lagrange dual. Okay, so it's a projected gradient descent algorithm. Otherwise, you can use the unprojected XU instead of the Y or Z, right? So this is just trying to make it consistent with just one notation XU and XP. Okay, so we'll take XU at T and project it on the set C to get XP at T. That's the idea. Okay. Now this is all fine. There's a small point here I have made. What is the stopping criterion? You keep projecting exactly using the figure that I showed earlier until some stopping criterion is satisfied. Now, what could be a stopping criterion? Well, we have talked about iterates not changing much, functions not changing much, but now with this, you can actually do better. You can have better criteria using Lagrange duality, in the form of something like duality gap. Okay, so just giving you some appetizer here. Okay, so this is how in reality you would compute the projection operator. Let's take a simple example. Let's assume that C is a set with just single constraint gx less than equal to C. In fact, in this figure, I have set even a simpler form, which is gx less than equal to 0. C has been set to 0 in this figure. Okay, so C is 0. Just make note of that. And the pink region is actually this constraint region. Okay. This is a constraint. Constraint region C. And the idea behind projection is you find m min of z minus x square such that gx is less than or equal to C. Yeah, just a small caveat here. I think I should just strike this off. This is not correct. So function being minimized is not z minus x square. That is basically the prox operator. The function being minimized is f. Okay, so in fact, what I should just cross out is this. F is a function being minimized. Yeah, that's all I meant. So you're trying to minimize a function f such that the constraint gx less than equal to C is satisfied. Now, what do you expect? Again, it's going to be very intuitive. If you are on the boundary of this gx, which is this boundary is basically gx, or in this case g1x, you could have multiple gx equal to 0. That's the boundary here. Okay, so if you are on the boundary, you would have slightly different condition, only slightly different than if you were inside. The thing is, if you are on the boundary, you're simply not allowed to go outside, right? The constraint is hard and binding. Therefore, in order to ensure that you're not able to further decrease the function value f while still honoring the constraint g, we have the second condition. Okay, so x is on the boundary of C, in which case gz equal to C and x minus z plus lambda of the gradient gz equals 0, which basically means that x minus z and lambda gradient gz are in the same direction. Okay, and this is the proximal idea. This is how the proximal projection is being computed, but this can be done for any function f. The proximal in some sense is like, okay, I mean in that sense it's correct. We overall function may not have been f, but in this specific graph the function we are trying to minimize is 1/2 x minus z minus x the whole norm square. Okay, so that sense it's correct, but this is simply from a projection perspective, this is simply one iteration of projection. So let me write that clarification. From projection perspective, please ask me questions if you have. One iteration of projection. Okay, so in that sense it's this is the f that we are trying to minimize in this particular episode. Okay, now let's go to the other part. The other part is when you are inside the region. Okay, the shaded region. When you're inside the shaded region, you're basically um, having gz less than c. Here you're free. You're basically free to have the gradient of the function going to 0. Okay, that basically corresponds to the gradient of the Lagrange function. Okay, so this is exactly the two parts. Okay, if you are in this constraint region, again I'm repeating, if you are in this constraint region, you can basically have gradient of f going to 0. If you are within the constraint region, I meant, if you are here in the boundary, then basically you're saying that gradient of f, in which in this case is z minus x, is basically in the opposite direction as the gradient of gz. Okay, this is gradient of f at z. Okay, please ask me questions if you have here. Um, okay, that's the
Uh,
intuition. Yeah.
could you explain the diagram once? What is it showing?
Yeah, the diagram, what we are showing is the region gx less than equal to 0. The shaded region is the region where gx is strictly less than 0. Okay, in this shaded region, gx, or in this case g1x, there's only one g, so I'll just use gx is less than equal to 0. Sorry, strictly less than 0. Okay, in this region you can have the gradient of f vanishing. However, on the boundary, you have to be a little careful. You're, that's where the constraint actually is active, right? So when the constraint is active, you cannot just insist that the gradient itself, gradient for f itself just vanishes. You'll have to also honor the gx equal to 0 on the boundary. Is that clear? On the boundary, you have to honor gx is equal to 0, right? So if the optimal point is on the boundary, then you will need this the second condition. Okay, so let me write this in words. This second condition, if the optimal point happens to be on the boundary. Is that clear? If
Yes.
the Yeah, but if it is not on the boundary, then you have the first case. Then it's a regular case. It's really a routine case. Okay, so I'm just going to write this in a different color. If the optimal point is not in the boundary, we have the routine condition, the regular condition, routine in the sense regular, basically it's like unconstrained optimization, right? Is that clear?
Yes, sir.
Okay, thanks. Yeah. Again, as I said, this is just to make sure that you have the tool ready in your hand to be able to solve this. I would strongly refer you to the optional material that I have. I'll be pointing you to uh, at the end for understanding this figure very completely. Okay. Otherwise, this could take probably a couple of lectures, at least one. Okay. So with that understanding, let's look at uh, gz equals c and z minus x plus lambda gradient gz equals 0. Let's look at the boundary conditions, right? What would they mean in a couple of these cases? I mean, I'm not going to do it. I will probably leave it to you. But basically, I'll request you to try this out for all these cases. What would they mean? Okay, for example, the first case, this would basically mean that A transpose X equals C and Z minus X plus lambda times A equals 0. Okay, so based on this, actually you could compute the value of or the relation between X and lambda at the in case the point is on the boundary. If optimal if X is optimal point, optimality point on boundary, right? Otherwise, it's just that else you'll have A equals 0, which that's only possible if A itself is 0, right? So anyways, you can try writing this for each of the simple cases. I would basically leave this as homework. I don't think I'll discuss this. In case you have um, any questions, do ask me. These are very simple.
Sir, I had one small question when still
Yes,
related to
please.
the diagram. Sorry about that.
Yes,
So,
yes.
what is the intuition behind the gradients of f and g being in the opposite direction?
Okay, very
Like there
good
was
point.
one.
That requires a little bit more work. It's related to the fact that gradient points in the direction of increasing value of the function, right? We are trying to minimize. So look at what we are trying to minimize. We are trying to minimize this function f. That means you want to move in the direction of decreasing values of f, right? And the
Right.
gx, if you move in the values of decreasing values of gx also, then you can satisfy the constraint happily, right? So if your point is on the boundary, that means you could not go inside the region while still minimizing the function. Okay.
So, like we have to stay on the boundary. That's the right.
Yeah. So let me write this point. If the point optimal point happens to be on the boundary, it means we could not decrease g, right? Uh, while also decreasing f. You understand? Which means gradients of g and f must have pointed uh, to in opposite directions. Okay, so this statement should help. So if the optimality point happens to be on the boundary, That means that there was no way we could have decreased G as while also decreasing F. And that's why it was on the boundary. That means the gradient should have been in opposite direction. Because if they're in the same direction, then you can decrease G as well as decrease F. I mean, or increase G as well as increase F. But they should have opposite tendencies. Is that clear?
Okay, sir, got it. I think this is a little bit clearer now.
Right, right. So this is a good question, by the way. But yeah, sorry to say that a very detailed analysis will require us to go through a couple of lectures, so which I'm trying to avoid now. Yeah, this is the case we are talking about. Case number 2. Okay. Case number 1 is straightforward, right? I hope that you have no questions on case number 1.
So case number 1 was pretty simple. I mean, it's just the usual.
Exactly. Okay, so these are some of the sets C which are easy to project. I mean, it's the projection operation. Geometrically, it should be mostly very intuitive, right? If you have a linear system of equations, basically a hyperplane, right? Then you can just the projection would amount to drawing a perpendicular from the point which you're trying to which is your update point, right? Let's say y or unprojected xu to a projection xpt. So that's very simple. Affine images, or many of these are simple. Um, Now you can just imagine that instead of um, just a hyperplane, you might also have had the entire region below, right? In which case, again, the projection, if the point is xu is already in the region, then there's nothing to do, right? So xu could have been here, in which case you have nothing to do. Let me show this case as well. Yeah. So this second case could be that you're here, xu, and you have nothing to do. You just stay here because you're well in the region. Okay, so you can do the same thing for norm balls. Most of the projection hard work is when you're on the when you're transgressing the boundary. Okay, here's a table of orthogonal projections. Um, so some of these are very intuitive, right? If you are in the positive quadrant, the first case, Rn plus, so if the constraint is a positive quadrant, all you need to do is basically make sure that if you're going outside that quadrant, make it 0, right? So it's as simple as somehow restrict your point to this. So if your point happens to be in this region, that's why it's called Z plus, right? So if this is Z, sorry. So if this happens to be the point Z, right? So you'll just basically project it so that you get rid of the negative component. That's a Z plus. On the other hand, a ball, the second case, this is R plus. If you're looking at a ball, I mean, the box is simple, right? Box is basically min max, right? You're just trying to restrict the point to between L and U. So you just do a shrink basically. Point is outside on the right hand side of U, you'll pull it to U. If point is on the left hand side of L, you pull it to L. If the point is inside, leave it as it is. Same thing with ball. I mean, the logic is very similar, right? So again, geometrically, all of you will get it if you're outside the ball, go radially into the ball. That the key is how do you go? You go radially into the ball. If you're already inside the ball, there's nothing to be done. Leave it as it is. So radial direction for projection. Okay. So pretty much all of these are very similar. I mean, simplex is basically the generalization of a triangle to multiple dimensions, and you can think of this, this n simplex as nothing but let's just show this n simplex. So imagine 1 0 0 0 1 0. So basically you'll take all these coordinates, and this is your n simplex. The operation is the same as everywhere else. You're just projecting to uh, the closest surface, right? So in this case, what all those expressions amount to is that if you're here again, go radially towards the center. Sorry, go orthogonally. In this case, orthogonally to the surface that is closest to it. Okay. Yeah, I'll probably not spend more time unless you have specific questions. This is geometrically they are very intuitive. Question is how do you derive it? Okay. How are these specific expressions brought about? Geometric intuitions are clear. Question is how these analytical expressions are derived, right? And that's where again we're going to just look at the Lagrange functions. I mean, we already saw the Lagrange function in some sense, but we saw it in a very intuitive manner, which is this lambda times, right? So basically, what we saw earlier, f plus lambda c or lambda g, right? And then on Lagrange functions and basically and KKT conditions. Okay, again, ask me if you have any intuitive questions here. Um, okay, just one point. If you can solve the projection step exactly, and efficiently, it's the same, right? I'm just trying to impress upon you that nothing has changed. So, I mean, if you have smooth, strongly convex, again, you get this log of 1 upon epsilon kind of convergence and so on. Okay, that's the best kind of we have. And you can also do, by the way, we get to the same using nested row with smooth and strongly convex. Okay. Okay, so the proofs are at the monograph by Sebastian Bubek. But in some sense, the proof for accelerated generalized gradient descent I've already given, so as optional reading, so that's good enough. So let's now go get to very quickly how to solve this projected gradient descent in closed form. Okay, I have given you some intuition, but now I'm going to give you the tools. And we're going to consider this generic problem. You're trying to minimize fx subject to gix less than equal to 0 for I equals 1 to m and hjx equal to 0 for j equals 1 to p. Okay, so these are the constraints we'll have. The variable x is in n dimensions, m inequalities, p equalities. Okay, so basically keep that in mind. N dimensional space with m inequality constraints and p equality constraints. That's it. Okay, if you have questions, let me know. This is the setting now. We are not assuming convexity to begin with. Okay, we'll bring convexity as required. So this is a general setting. In the in the case of projected gradient descent, what would fx turn out to be? Anyone? What would fx turn out to be in the case of projected gradient descent? One particular epoch of projected gradient descent. Yes.
Half into the L2 now.
Yes, exactly. So it is just 1/2. So z is fixed. 1/2 z minus x norm square. That's it. Okay, now you'll solve this iteratively. But if you could solve this exactly, that's also fine. The issue is fx may be all sometimes very complex, and you may just do a gradient descent or accelerated gradient descent on f through z, right? And then solve the simpler problem, half norm zx minus z minus x square. Um, right. So the both options exist. So in this option, you do this instead. Right, so I'll just write that down for the bigger picture. Instead of solving the constraint optimization problem iteratively by gradient descent on f and then proximal or other projected constraints, if the f is itself simple, one could solve this constrained optimization problem directly, or one could attempt to, or that's all we can say. Okay. Okay, so I just make this very clear. This what we discussed is so far option one, and in both cases, what we are discussing will be useful. And I've just highlighted an option two here. Okay. Okay, so let's write down the so-called dual theory. So given the fx and these constraints, you can now form the Lagrange function whose motivation I had provided through that simple, figure. If you are inside the region, f is good enough. If you are on the boundary, then you have to start honoring the constraints, the gradients of f and the gradients of gi's and the gradients of hj's should basically have some relation, basically. And it is basically that the gradient of f should lie in the same space as gradient of the space spanned by the gradients of GIs and HJs. That's basically the idea. So instead of saying they're opposite direction, now you're saying they should be in that space band with some sign constraint. Okay, so that's the reason we are bringing this Lagrange. Okay, so rationale behind at the boundary Lagrange function at the boundary, the gradient of f must lie in the space spanned by the gradients of g's and h's with some sign constraints. So I mean, you remember that g's gradient of g and gradient of f should be in opposite direction. But now when you have multiple gi's, you're basically saying that this lambda should all be positive. That's it. So that's the sign constraint part that I've additionally brought in here. Okay, some sign constraints. And this is the sign constraint we're talking about. Okay, so now you can easily show that for every feasible x. What do we mean by feasible x? Feasible x is exactly those x's for which these conditions hold. This is called a feasible region. Okay, it's called a feasible region. Okay, so for every feasible x, if you fix the lambda i's, which are so that the directionality is taken care of as discussed earlier, you can show that fx is greater than or equal to this Lagrange function. Why? Because the Lagrange function has lambdas multiplied by negative GIs. Okay, so positive lambdas multiplied by negative GIs. Okay, so this is what into negative GIs. Okay, which will obviously be negative. And then mu's are multiplied by h, which is all going to be at the again in the feasible region. Mu's will be multiplied by h, which are all zeros. Okay, so again, no issue. Why? Again, remember, we are talking about feasible region and not some arbitrary region. Okay, so this is all about feasible region. Okay, so therefore, what happens? These two terms are anyways not positive, non-positive, and as a result, fx will be therefore this part will be greater than or equal to L of x comma lambda comma mu. Is this clear to everyone? Please ask me questions if you have it with respect to this inequality.
Sir, this is I guess, a silly question maybe, but
Sure.
like, what is the point of adding h to the equation if it's just all zeros anyway?
It's zero only at the feasible x. That's why I'm highlighting at feasible x. The idea is to formulate it such that you're pulling the points into the feasible region. You have something to deter the points from becoming infeasible. So this is at feasible x. Is that clear?
Okay, so it's like
Not
a kind
everything.
of an evolving. Yeah, right. Okay, okay,
Yes.
understood.
Very good question. Yeah, we cannot be ensuring that throughout, right? I mean, why would we need projected gradient descent if the constraints are always satisfied, right? So the constraints are getting violated, therefore we project. So the feasible x is when basically you're saying the constraints are satisfied. Is that okay?
Yeah, understood, sir.
Thanks. Okay, so now what we do, our most favorite thing, right? If you have this inequality, we'll say, well, if we have an inequality, we and the right and the left hand side of the inequality does not have any lambda or mu, right? So you notice that left LHS has no lambda or mu. Okay, RHS on the other hand has lambda or mu. Now what are we going to do? The first thing is, well, the RHS unfortunately has x. Okay, so RHS has x. Okay, but if this holds for all lambda greater than or equal to 0 and blah 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 in the feasible region, basically, or feasible, I keep on repeating the point feasible x, then even if I minimize the right hand side with respect to x that are feasible, the inequality will still hold. Okay, so that's the idea. Inequality will hold even if I minimize the RHS with respect to all feasible x. Okay, so that's all we have done. Um, this minimization gives you the so-called dual function. Okay, this is the dual function. L star lambda mu. Now the RHS has no x. Okay, this new RHS has no x. So now we have something interesting. What happens if you tighten the gap? What if you make the LHS minimum with respect to x and the RHS maximum with respect to lambda mu? Okay, so that's the basic idea. So the idea is that you would still have, if you say min over x. Now we'll x feasible. Okay, so you'll have to keep saying x feasible. Well, do you have to say x feasible? Maybe it's a question for you. Um, Min over x feasible certainly, but should it be min over all? Let's think about it. Should is greater than equal to max over the um, um sorry, I did yeah, max over lambda mu. Now what lambda should be? Mu should be, you should keep in mind lambda greater than equal to 0, mu could be anything of this L star lambda mu. Okay, so this is an interesting inequality. And this motivates the dual optimization problem, which is um, the one we are seeing here on the right hand side. This motivates the dual optimization problem. Okay. Um, Max over lambda in Rn subject such that lambda is greater than equal to 0. Mu could be anything of L star lambda mu. Okay. And this inequality held was for all primal feasible x. So it probably makes sense to retain that primal feasibility and on the left hand side, min over x feasible, right? So what are we saying? Basically, we are saying we have a new optimization problem. That's a dual problem. Okay, and that again has a geometric interpretation. It's detailed understanding I have in the optional material. But basically, what's happening is, I mean, you can state the dual problem in multiple ways here: max over L, or max of L star, or you can write it in terms of max over min of L, because L star itself was this max over min of L. Okay, this part was defined right in terms of max over min of L. I'm sorry, I should just only this part here. This is L star, the definition of L star. Okay, it turns out that this is basically as follows. It's like the dual problem. What you're trying to do is trying to um, push a hyperplane beneath the surface above. There's a surface above, and that's the primal surface. You're trying to push the primal surface down. You're trying to right, the pushing of this intercept um, is the primal optimization problem. Okay, so primal optimization problem amounts to saying, okay, I want to push this down, uh, down in the sense pushing it down here. Okay, It's difficult to show in this big in this plot. Primal or original. Primal is basically the original. Is about pushing down the y-intercept of this region. This region is basically like your epigraph. This epigraph like region. It's not really epigraph, but okay. I mean, to know what that exactly is, I'll have to again take you through the entire discussion. But I think it suffices to show that there's some pushing down happening, and the dual optimal is about pushing up the hyperplane, the y-intercept of the hyperplane. Of the hyperplane. Now, what is this hyperplane? It is the tightest supporting hyperplane. We have seen tightest supporting hyperplane when we defined subgradients, right? I mean gradients and subgradients for convex functions. So we are saying the tightest supporting hyperplane, if you consider, then its y-intercept is what is the dual problem, and you're trying to pushing it up. So one is about pushing down, the other is about pushing up. And when do you think the two will meet? The pushing down and pushing up. Any thoughts? It's practical. It's somewhat evident. Sorry, it's somewhat evident in this figure. When do you think the two will meet? These two, right? The dual problem, where you are trying to say this part, right? This in red. That's what trying to push up. The part in gray, you're trying to, the part above, you're trying to push down. When will the two meet? Any thoughts? Did you follow the question?
So like this is sort of like a tangent supporting hyperplane. That's the point where they meet, and
Yeah, yeah. Here, see, do they meet in this case? In this case, the tightest hyperplane. Do you see a gap here?
yeah, there is a gap between them in the figure, but like I'm not sure if they're meeting. Uh,
They are not meeting. In fact, this y, I'm talking about y-intercepts. The two y-intercepts don't meet, right?
no,
Right. This is called the duality gap. So the two intercepts, two y-intercepts, when would you expect them to meet? Uh, for what kind of shape of I? Does I look convex here? What kind of shape
no,
of I?
no. It's not convex, right?
Yeah.
Like
But if it's convex, do you expect it to expect them to meet? The supporting tightest supporting hyperplanes y-intercept. I can just show that example, right? So imagine you have this as I. Okay, then um, so imagine that your I was like this. Okay, oh, I was like this, and it had a y-intercept, and then you have this tightest supporting hyperplane below, won't you expect it to meet exactly at the y-intercept? I'm not able to show it properly. There is one satiety supporting hyperplane which meets at the y-intercept, correct?
In this figure, yes.
And that's true in most convex, unless it's open. If the convex set I is unless when the shape of I is convex and closed. Okay, so there is a small catch here. Oh, convex and closed. If it's closed, then you can expect there to be zero gap. These two will meet. Is that making sense? Again, this is for lack of time, I'm just trying to give the quick intuition. For more details, you'll have to look at the derivation, which takes probably a couple of classes. But I hope this intuition is clear to everyone.
So we can say that in the convex case, the intercepts will meet. Otherwise, no.
Yes. Otherwise you can't say no. Otherwise, it looks little difficult, right? It looks quite difficult.
Otherwise, it's not guaranteed. In
It's
the
not
convex
guaranteed.
case, yeah.
If it's closed and convex, again, closed is important. If the boundary were dotted, you couldn't have expected this, right?
Right, right.
Yeah, please ask questions. I mean, you can ask very intuitive questions at this point. Okay, so all this leads to the following. This is basically the holy grail. These conditions called Karush-Kuhn-Tucker conditions are necessary if you want zero duality gap. Again, what's zero duality gap? Oh, sorry, this was coming down. This has gone down for some reason. Um, the 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 gap between the primal and the dual here, okay, is called the zero duality gap. So theorem basically it has gone down for some reason. The theorem basically says that the solution to primal, okay, let's call this P star, and solution to dual, let's say this is called D star. Okay, so solution to primal P star will always be greater than equal to, as you see in this plot, greater than equal to the solution to D star. Okay, and this P star minus D star is the duality gap. So theorem is just that solution to primal is greater than equal to solution to dual, and this P star minus D star, which is guaranteed to be positive, is the duality gap. It's called the duality gap. Okay, so a lot of analysis is when will this duality gap go to zero? Because that will give you a solution. That will give you a solution for the lambdas and the mu's, which are commensurate with the solution for x. Okay, so it turns out that the holy grail, this Karush-Kuhn-Tucker conditions, are necessary conditions for zero duality gap. And what is it? Basically, now these can be used blindly. I mean, many people do use them blindly without understanding what they're doing. But these are necessary conditions. So if they hold, or rather if x hat is a point of optimality and is also dual feasible, then there must exist lambda high and g mu I that satisfy these conditions. That's basically the I mean, let me state that, right? What are we saying? The sufficient condition says, the necessary condition says, if you're trying to minimize, right? So same old thing, min over fx, such that Gix is less than or equal to 0, Hjx is equal to 0. This is optimization problem. And if a solution, if x hat is the argument over the um over such x, if x hat is argument over the x over such, then there should exist, then there must exist lambda hat and nu hat and following conditions. With the triplet, which is x hat, lambda hat, mu hat. Okay, that's a necessary condition. Is this clear? What are those conditions? It's basically saying the first condition says that the gradient of f is lying in the same space as the gradients of gi's and hj's. However, the third condition says the lambdas that help you span that space should be such that they are greater than or equal to 0. That means a gradient of f should not have any component in the direction of the gradient of the GIs. It can have a component against the direction of the GIs, which is what we had kind of given an intuition about. So that's the condition number 3. There's also something interesting 4, which 4 says that either you're on the boundary, in which case the lambda is effective, or you're inside the boundary, right? In which case lambda is ineffective. The third condition says either you are on the boundary, gi x hat equals 0, and therefore lambda I hat may not be 0, right? Plays some role. It may not be 0. Or you are inside, well inside, right? The space, which is gi x hat less than 0. And therefore lambda I hat is meaningless. I mean lambda I hat is 0. Basically, plays no role. Okay, this is often also called the complementary slackness condition. Okay, the rest are just feasibility. So if you look at gi x hat less than equal to 0, this is what we had been marking in red earlier, right? This condition, gi x hat less than equal to 0 and j x hat is equal to 0. These are simply feasibility conditions. You want them feasibility, right? Primal feasibility. Okay. Uh, any questions? Let me know. Otherwise, we'll proceed. This is the necessary condition. Does this require convexity? Did we talk of convexity anywhere here?
When we were discussing how to make the duality gap 0, you mentioned that it's guaranteed for convex, but other than that, we've not discussed.
Ah, yes, very good point. So if it's guaranteed in the sense, if it's convex, you would expect convexity to be a sufficient condition, right? Sufficiency condition. You would expect convexity to be a sufficiency condition, correct?
Right, right.
But not necessary. I mean, convexity is not in the necessity part. If the if these conditions hold, then you must have zero duality gap. Hmm? Okay. However, they are part of sufficiency condition, exactly as you pointed out. That's the next part. KKT conditions plus convexity, they they imply the zero duality gap. So this is sufficiency. Sufficiency owing to convexity. So what are we saying here? If the function f is convex, gi's are convex, edges are affine. Well, we say edges are affine because we, in some sense, they are equality constraints, right? You could have non-affine edges which also lead to convex sets, but we can be guaranteed that with a convex f, gi is being convex and edge is convex, you basically are dealing with edge is affine. You're dealing with the convex sub-level sets. Okay, and this function will be convex. The Lagrange function will be convex. Okay, so if they are if this holds, that's basically convexity. That's exactly what I'm talking about. If convexity holds, right? Then the KKT conditions are necessary and sufficient. Well, we already seen that they are necessary, but with this you get them to be necessary and sufficient as well. So convexity adds a sufficiency part. Okay, the conditions are exactly the same. I've just called them equation 6 again here. No change. Both are equation 6. Any questions? So my point is all the projection operations in that table we showed earlier can be derived using these KKT conditions. Okay. The algebraic expressions, right? So these KKT conditions are very powerful. Okay, so I mean you can try it yourself. It's not a big deal. Okay, any questions? All of these have to be simultaneously satisfying. It's not an or, by the way, it's an and. Okay, so I mean you can try on some more linear programs. You can try what we'll have is C transpose X as objective, constraints as AX less than equal to B. The L star again turns out to be linear. Okay, the dual function it will generally be of the same complexity as the primal. You can't expect that the primal is a quadratic function and dual becomes linear suddenly. The dual may become simpler quadratic if the primal is a quadratic. It's possible, but the form of the dual may cannot change drastically. So you can't have linear becoming quadratic. Okay. So after all, you're, I mean, otherwise, solving the dual problem would just yield you unnecessary mileage. Okay, so you'll see that quadratic program. Objective function is quadratic. The dual is also quadratic. Nothing has changed overall in the form. The number of constraints could be different. So in the constraints, in the primal constraints, ax less than equal to b, the dual constraints have become very simple in the quadratic case. Much simpler quadratic constraints. Right? These are examples of simplified constraints in dual. Okay. Um, yeah, I mean, I also talked about when strong duality holds. Strong duality will basically mean that zero duality gap. Okay. Strong duality, it means that, okay, you can solve the dual problem, but the dual problem is going to give you the same solution as a primal. Okay, so strong duality will mean zero duality gap. Okay, and we talk about conditions under which holds. For example, in linear programs, if you have feasible primal and dual, then zero duality gap holds. With quadratic, it always holds. Entropy is a different thing. Now you have xi summation ln xi, but now in the dual you have an exponential form. It's similar complexity. The form has changed, and from a computational perspective, it's possible that the dual is more efficient to solve. That's very much possible. Okay, so let me just make that the form of the dual and the primal are the same. However, the dual might be computationally easier to solve than the primal, or vice versa. It's also possible the other way. Computationally, because of the number of constraints, because of the nature of sparsity and so on, right? So maybe there are many of these which are just going to zero. That's also possible. Many of the variables just might go to zero. Okay, so I have extra optional material from previous offering where I talk about geometric interpretation of necessary conditions of zero duality gap, connection with convexity, lots of results on weak and strong duality theorem, and Slater's constraint qualification. Based on this, I also kind of evolve into other algorithms in the conditional gradient descent, convex conjugate as another notion which we didn't talk about, dual ascent, ADMM. So lots of algorithms that operate, interior point methods. I mean, many things that I talk about otherwise, right? Um, so you can feel free to, I've put the links to the YouTube. You can certainly feel free to watch them. What I've done as a self-study material, which I'm not going to go over in details at all. I mean, let's take the example of support vector regression. Okay, can you compute its dual? How do you what does a dual look like, right? So I've actually worked it out in details because it's a practical machine learning application. So this is the original. This is a primal, right? So how do you go from the primal to the dual? What does the Lagrange function look like? And yeah, what does the dual problem look like? And then what are the KKT conditions? So I write down I derive all the KKT conditions which you are very welcome to try and derive. And then you can also inspect what the geometric intuition of these KKT conditions is. What's the notion of support vectors? Okay, KKT conditions clearly hint at support vectors, or not just hint at, they outline the support vector. And yeah, so on. So I've just kept them so that you get a complete idea of what the dual object. Now, so you can also actually derive the dual objective. There's weak that also is shown here. And when do you have strong duality? Okay, so we also talk about strong duality here. And what is a dual optimization problem? How can you solve it efficiently? Some of that, and then how it also gives rise to the notion of kernel functions. See, the dual is also interesting because it just gives you a very different view of the problem, which you didn't get easily in the primal setting. Right, so I've given an example of kernel. So it's very interesting use case. Oh, sorry, that figure didn't come up. I'll make sure it's there in the final slides. Okay. I've done the same thing for ridge regression as well. In ridge regression also you can come up with a dual and then kernelized dual and so on. Yeah. Okay. So I would probably now move to the discrete optimization unless you have questions on this part. Maybe just 15 minutes we'll do the discrete optimization part. Any questions? We'll now move on to submodular optimization. Can you see the slides? Are they visible?
Yes, sir, they're visible.
Okay. I'm assuming there are no questions on the previous part. Okay. So we had given this big picture of continuous and discrete optimization. Um, Now the discrete optimization itself requires a lot of discussion, but I'll be talking a lot only that aspect of the discrete optimization which fits into very interesting, exciting areas associated with machine learning. Okay, so otherwise optimization itself can take ages to discuss, but we will focus on ML related discrete optimization. We're also giving a hint of what the other areas would be. Okay. Um, so one important point here is that whether it's data or features, we are often interested in subsetting. So here is this V, this entire set is called the ground set. Okay, this entire set, okay, is the ground set. And what we are looking at is a function that goes from every possible subset, that is goes from the power set of V to R plus. So it is going to evaluate every subset. Okay, f on s, f on s prime, and the function will score a subset so that that subset which is most effective from a particular objective point of view is picked up. An example is summarization. If you have lots of images, I want a subset of images which very well represent the entire set of images, right? So this can be obtained if you have a good function and if you're able to optimize that function. Okay, so there's a lot of useful material on this. Professor H. Narayanan, who was retired from our own electrical engineering department, has talked a lot about submodular functions, electrical networks, and unfortunately, you won't find any ready-made textbook on ML aspects. So very less. Okay, unfortunately. Um, very less ready to use textbook, right, on ML aspects. And I would say even discrete optimization. Okay, but these are useful anyways. Also some acknowledgements. Some of the slides have been borrowed from submodular optimization course at University of Washington by Jeff Bimes. Of course, they've been inspired. We also have a bunch of tutorials. Professor Rishabh Iyer and I have been giving a bunch of tutorials at ICHI, and then we had a tutorial at AAAI this year as well. There are also tutorials in by um, Stephanie Jegelka and Andreas Crosse, Jeff, in fact, also gave a tutorial on submodularity long back. So yeah, these are all useful material. So let's move on to all the different aspects of discrete optimization in machine learning. Um, just a listing, right? If you have probabilistic models and you're trying to find the best configuration, that's a map maximum posterior inference in probabilistic models. Feature subset selection. I give you some of these examples early on. Data summarization, natural language processing, computer image segmentation. So recap examples from our initial lecture. So just to kind of recap. And all had this notion of subsets, right? But you want to score those subsets in a very effective manner. So what we'll talk about is the definition and intuition of submodularity. We'll begin on that today. And show the modeling power of submodular functions, and then of course move on to applications in machine learning. Okay, so just want to make sure we have time. Yeah, we are doing well on time. So the combinatorial subset selection problem is that going over all the elements or all the elements of the power set, which is all possible subsets, is very expensive, right? So here's a subset I have chosen of apples, bananas, and books, and somehow the score has been given to that subset of the score value is 22, right? So what is a structure that the problem can lend itself to efficient solution so that I can find the right subset with the best score? And that is submodularity. And the canonical example of that is the number of distinct colors of balls in an urn. So on the left hand side, you see, okay, I'll go over this a little slowly. So think of this as our set A. Okay, this is set A, and the set A has two brown and three green balls. The set B has two brown, in fact, those two brown balls, three green, and two blue balls. Okay, so in this sense, um, B is a superset of A. Okay. Let me just use different colors. So this is A, and and this is B. Now what I'm going to do is add this additional ball, which is the V. So I'm adding a V to both A and B. Okay. Um, and I'm going to measure um, the additional number, the increment in the number of balls, right? So initially, the f of A was what? It had exactly 2, right? F of A was 2. What was f of B? It was 3. There were 3 distinct colored balls, or 3 distinct colors of the balls in the urn in B, and 2 distinct colors of balls in the urn in A. Now when I add the blue ball, you can see that A has benefited in terms of the function f is an additional color, whereas B has already 2 blue balls, so therefore this third blue ball didn't make a difference. Okay, so f of A union V in the first case is 3. F of B union V in the second case is 3. Nothing has changed. Okay, so then what we are saying is f of A union V minus f of A, which is 1, that is greater than equal to f of B union V minus f of B, which is in this case 0. Right? This is when A is a subset of B. Okay, so such functions are called submodular functions. Basically, you can think of these functions as functions with diminishing returns. Okay, so what's happening here is as I keep adding balls, the first time I added a ball, there was some gain, then little less gain, then more. So as I keep adding balls, obviously there'll be saturation. If you're fed something, right? The first time you're fed a sweet, you may be very hungry. You may see a lot of value. The second time you're fed the same sweet, you see diminishing returns. So this is the diminishing returns which you see in data sets. Now, your data set as it grows by a factor of 10, 20, 30, a lot of redundancy is seen. The redundancy only grows. So that's why you see diminishing returns. So this is very commonplace in real world as well as in machine learning. Please ask questions if you have. I'm going to go a little slowly on this part.
So the functions that show this diminishing return,
Could you repeat a little loudly?
that the functions that show this diminishing returns are called submodular functions.
Right. In this form, the functions that show diminishing returns in this form are called submodular functions. Exactly. So let me ask a question. I mean, you can also ask me questions. I'm going to also pose a question to all of you. So my question is as follows. Is it necessary, okay, for a submodular function f, okay, that f of a is less than equal to f of b if a is a subset of b? So is it necessary that submodular functions will monotonically increase in the size of the set? That's what I'm trying to ask you.
No, sir, not necessarily. There are submodular functions which are not monotone, I think. So if it's monotone submodular, then we get some pretty good properties, but it's not
Yeah, you
necessarily monotone.
okay. Can you give an example? Give me a counter example to show that it's not
It's
necessary.
a little hard to think of right now, but I've seen some examples before.
Okay, so I'm going to give that as a homework problem. It's very important to let this get internalized a bit. So I'm going to leave that as a homework problem. Um, uh, either prove, either prove or disprove using a counter example. Okay. Um, so in general, some modular functions have this, right? So if you have some fries and you have some drink with that, you'll see that the cost, incremental cost of procuring the next item in in eatery is diminishing, right? So as you keep stocking that, that's exactly what the big malls and the DMarts of the world are leveraging. The more items you buy, the more the discount. Modular function, on the other hand, each element just has some weight, w. Okay, so the function f is simply a sum of the weights on the elements of the set, right? So it's not that as you keep buying more items you get more discounts. No, that doesn't happen here. um, you kind of get linearly growing with the number of elements. You can think of these as linear. I mean, these are counterparts of linear slash affine functions. in the continuous optimization, right? Okay. So I had asked this question earlier on, and that's come up. There's something called a monotone submodular function. A set function is called monotone or monotonic if as you grow the set, right? In the subset sense, right? Not just the size, but actually A becomes subsets of B, which is a subset of V, then f of A will be less than or equal to f of B, right? That's a monotone influence in social networks, right? What increases monotonically in social networks? Influence. I mean, the more the number of friends you have, the more influence you have. It could be submodular, that's another thing, but it may show diminishing returns. That's what I'm saying. That's what I meant by submodularity. But it is monotone. It's increasing. Discrete random variables, you'll find that the entropy is monotonic. Okay, you can try this out. This is again something you should try. If you have discrete random variables x a comma xc, right? Then you can show that as you add a new random variable, what happens, right? There is a monotonic increase in the end. Okay, so try this out. Now, question I have is, I mean, it looks like entropy is monotone and possibly entropy is also submodular. Does that prove that every monotone function is submodular?
Uh, that would be a very sweeping statement. I don't think that would be true. Like if it's monotone, it's not necessarily submodular.
Yes, it doesn't, right? Still not mean that there is no function that is submodular but not monotone or vice versa. Okay, so maybe you can give some thought to it. I think we have exceeded the time by 1 minute. So I'm going to leave you at this homework problem. Again, I'm repeating the homework problem. Um, just go back to I'm pasting this problem again. You need to prove that if you have a function which is submodular, then is it necessary that it is monotone? Okay. Thanks for your attention. We'll meet on Monday. Is there any other last question anyone has?
Sir, so monotone function, a modular function can also be monotone, right? So that is an example that can be.
That's a good point. A modular function, it can be monotone if the weights are all positive, right?
Yes, sir.
Right. That's a good point. Yes. If a modular function has non-negative weights, it is it will be monotone. Good. But then some modularity, you'll need to think a bit more, right?
Yes, sir.
Okay. Anything else? Or should we close? Okay, then thanks for your attention and thanks for adjusting to this new time for today. We'll meet at the regular slot on Monday at 2 p.m. Thanks.
Monday would be offline.
Monday will be offline. I will meet in the class. Only today was an online, purely online. Monday will be offline plus online. I mean, people can join. They are not physically on the campus. Thanks. But we prefer so the institute wants everyone to join offline. So please do attend classes offline starting Monday.